want to give you a very brief presentation, and then my colleagues, Dr. Steve Gwynn and Dave Cooney, will run through a live demonstration. So I'm going to zip through some slides before we get down to the real part of the show. Oops. Okay, so Exodus, as we heard the other day, is a suite of evacuation modeling tools that have been designed to simulate the human behavior and movement of large crowds of people in complex structures. We started the research and development on the Exodus concept in around about 1989, and Exodus has generally been available to the public since 1996. We now have users in 23 countries around the world, and there's several hundred licenses of Exodus around the world. We've got the types of software we've got are building Exodus for the built environment, maritime Exodus for the marine environment, air Exodus for the aviation environment, and the VR Exodus, the post-processing tool, VR Exodus. We heard earlier today, or yesterday, that the model looks at people-people, people-fire, and people-structure interaction. I'm not going to go into this in any detail in the presentation. We don't have enough time, but we've written over 100 publications on this sort of stuff in the peer-reviewed literature, so you can find out all the details about how the software works in detail through the literature. We've also used the software in a number of prestigious projects around the world, from the Airbus A380 design to the new Airbus flying wing concept, the Millennium Dome, the CVF new aircraft carrier program for the Royal Navy, and so on, a number of different types of applications. The software has also been recognized through the award of a number of national and international awards, such as the IST Award, European Award, the Queen's Award, BCS Award, Royal Institute of Naval Architects Award, and so on, a number of awards for the development of this software. In developing the software, it's important that we have access to realistic data. And it's not just, anyone can build computer software. It's almost like building a computer software game. What you really need is an insight into the behaviors that you're trying to simulate and access to the data. And we've been running a number of full-scale experiments, from looking at how people behave in overturned railway carriages, in evacuating hospitals, in our ship simulators, in full-scale ship evacuations, in aircraft filled with smoke, and most recently we've been working on the World Trade Center and looking at the behavior of people in the World Trade Center evacuation. I'm going to talk a little bit about that in a couple of minutes. What I'm going to talk about and run you through very quickly are some examples of the Exodus software in action. Now, this is some work we're doing in San Francisco using the Building Exodus software, not for evacuation, but looking at circulation. So we're looking at the underground stations in San Francisco and looking at the crowd movement in these stations. On the lower level of that station, we've got trains arriving and disgorging passengers, passengers going onto the trains, and passengers coming off at street level, and so on. And we're looking at how the people move around that station and what's going to happen when they double the number of people using that station. How can we improve the layout for when we double the number of people? So we're using this in a pedestrian analysis, as a pedestrian analysis tool, not as an evacuation tool in this case. Here we're looking at a large public event. This is a city centre concert, and we're looking at the people arriving in the city square from this railway station and different parts of the city, and we're looking at the congestion that develops in this square. What you're seeing here is the 2D Exodus view, where you see the people as dots moving around. When the screen changes colour, we're now looking at population density. So this is the number of people per square metre. And so where you see the red areas developing, you're getting into high-density crowd situations, and possibly you may have a problem there if this develops, and certainly if you had to evacuate this area, you may have problems in those areas. But other things we looked at is what happens if you now shut down the railway station, which is bringing people into the square. Say there was an emergency and you had to control the crowd, and the police wanted to shut the railway station. How long would it take for that to have an impact on the crowds developing in the square? Another thing we've been doing, we've been working with the Beijing government. We're helping them with the 2008 Olympics. And one of the issues that they're concerned about apart from designing their stadia, are terrorist actions in Beijing. And here we're looking at crowd management in Wang Fujing Street, the largest, busiest street in Beijing, shopping street, up to 800,000 people a day, peak throughputs. And what we're looking at here is an incident that's happening, a terrorist action somewhere along the street, and we're looking at how the people may evacuate as a result of this. And one of the things that we're seeing here is the response time attribute at work, and we're not simply imposing a response time. People are communicating to their neighbors the need to evacuate. People in the immediate vicinity of the incident know an incident has taken place, and they start moving, and it's when they pass other people in the street and they convey to them that there's a need to evacuate, they start to evacuate as well. So it's actually quite a complex system that we're simulating here. I want to show you some examples in aircraft aviation. This is some work we've been doing on the A380, the Super Jumbo for Airbus. This is some early work we did looking at evacuation from a double-decker aircraft, looking at issues about how long it would take to evacuate the aircraft, using, in this case, all the available exits. But we're also interested in situations where you've got half the normally available exits and different exit combinations and so on. So it's quite a large aircraft evacuation situation. I want to briefly talk about integrating fire modeling and evacuation modeling. We heard earlier this morning about some work we've done in ship calculations. This is an Exodus reproduction of the Manchester aircraft disaster. We're actually taking real fire data produced by the FAA in the United States, and we're imposing that on this model of the Boeing 737 at Manchester, and we're opening the exits to the same sequence that actually happened in the actual incident. And we're looking at what might happen during that evacuation. One of the things that we calculate here is the number of fatalities. And we predict, on average, we get about 57 fatalities for this particular incident. The number of people that actually died at Manchester was 55. We're seeing about 57 on average. And the location of the fatalities is reminiscent of what we actually saw at Manchester. I now want to talk about building evacuation and building exodus. And for Jake, this is one of the things you were talking about in your presentation. This is the staircase flow graphs. We've been running simulations of the World Trade Center evacuation, and we've done several types of what-if simulations. We've looked at what would have happened if there were 7,000 people in the building and they had to evacuate, and what would happen if the building had a full population of 25,000 people and had to evacuate. This is one of the flow graphs that we've generated, the vertical axis being the floor number, horizontal axis the time, and we're looking at the first person off each floor and the last person of each floor in the case of the 25,000 person evacuation. There's a lot of information in that diagram which I haven't got time to go through. But I want to talk a little bit more about these calculations because I think they're fairly interesting. We've been running the World Trade Center on a 266 gigahertz Pentium with about 4 gigabytes of RAM. The scenarios we've looked at are 25,000 people in the building distributed over the floors. We've also looked at 7,000. Why 7,000? Well, it was estimated there were 7,000 people in the building at the time. We've also done a detailed analysis of interviews with survivors from the World Trade Center, and from that we've deduced response times. And what we've done in these simulations is imposed the response time distribution that we've already collected from the information that's available in the public domain. And it's interesting to see that to run the 7,000 person calculation on the 266 gigahertz Pentium takes about 8.5 minutes of runtime. Looking at the 25,000 person case, it takes between 1.5 to 2 hours to run that simulation above the 91 floor. Let's write them off because the staircase has been cut. That's imposed the actual response time distribution. Now, how long would it take to evacuate the rest of the building? Well, we predict that we can evacuate the rest of that building in 2 hours, 3 minutes with that load of people in there. In the time of WTC